Happy Question Show Day. As always, your questions, my answers, wherever you are across my channel, if a question pops in your brain, just write it down. I will gather them all up and I will answer them here. Now, someone asked me, like, where specifically should you go to ask a question? Anywhere, on any video, all 985 of them. YouTube has a gadget that lets us see the new questions, so as you know, I will catch all the new questions and then gather them up. So, but generally it's safest to post your question on the most recent QA, but really, seriously, anywhere, I read them all. Once again, we've got another special guest answerer. It's astronaut Mike Massimino, who answers a question about the training that astronauts receive. But let's get into the questions. I'm in Dogtuin. Can we still live if the sun dies? Yes, for a while, although I wouldn't really call it living. So let's imagine you've got this far future and the sun turns into a red giant and gobbles up Mercury and Venus and scorches the surface of the Earth and then compresses itself back down and becomes a white dwarf and then just cools down to the background temperature of the universe. Can we survive that? Well, like on the surface of the Earth, as the sun is heating up, it will boil off all of the water off the Earth, it'll wreck the atmosphere, it'll make the surface of the Earth completely unlivable. So we wouldn't be able to survive in the way that we do now with trees and animals and oceans and things like that. But if you went underground and you had your own source of heat, maybe you use, say, geothermal energy from inside the Earth, you could last for a really long time. You could turn that geothermal heat into electricity. You could last for millions and maybe even billions of years as the Earth slowly cools down to the background temperature of the universe. So, but you would need a lot of technology. The thing with here on Earth is that the sun is putting all this energy in, it's making these trees grow, and we can just kind of go on year after year without a lot of technology. But to be able to survive after the sun dies, you'd need some pretty advanced technology. You would have to keep it working, and you could never really go back to the surface of the Earth. So I wouldn't think it would be very fun, but if you had no other choice, I'm sure our technology could figure out some way for some people to survive after the sun died. Nicholas Bolding. Let's assume something catastrophic happens and essentially stops any and all supply missions to the ISS. How long approximately could they live for? And what would happen first? Asphyxiation, starvation, thirst, or something else? So the International Space Station is reboosted by the attached rockets that are connected to it about every 90 days. And the longest that the International Space Station has ever gone without any kind of resupply was back when the Columbia disaster happened. And you had some periods where it was about 4 months that nobody delivered anything to the International Space Station. So that is sort of the longest that has ever happened. Now you could imagine it going longer than that. Maybe it could go to from 4 months to maybe 6 months. But at that point, the astronauts would absolutely be running out of supplies. And it would really just be a race. They've got their carbon dioxide scrubbers, which makes sure their atmosphere is breathable. They've got the water that they can drink. They've got food. They've got and just the oxygen in the atmosphere. And then the other problem, of course, is that the International Space Station is slowly descending in its orbit. And if it doesn't get reboosted, it's going to fall more quickly, and eventually it's just going to burn up in the atmosphere and fall apart and be completely destroyed. So which of those is it going to be first? I don't really know. I would say that it would probably be the re-entry first, but I actually don't know which one is going to be the one. It would really be a race. If the carbon dioxide scrubbers went, that would kill them very quickly. If they ran out of food, obviously they would starve, but they could go for months before they completely starved. Man, it's awful. I hope it never happens. Richard Price. Hi again, Fraser. I've asked you this before, but you may not have seen it. Why was the main fuel tank on the first launch of the space shuttle white, and why did they change it to the brown color later on? This has been bugging me for years. Well, this is going to be easy. I'm going to be able to help you relax. The first launches of the space shuttle, they painted the fuel tank that white color. And then later on, they realized that they didn't have to paint it and that they could save a few 100 kilograms of weight. And so that orange color that you see is actually just the color of the foam insulation that surrounds the space shuttle main fuel tank. And didn't really change the way the the insulation kept the fuel cold and saved them a couple 100 kilograms. And that's a lot. Like when you think about the fact that the space shuttle cost like $10,000 per kilogram to launch into space, to be able to save a few 100 kilograms is pretty significant and less effort. So that was why they did it. Louis Tiexito. Hey Fraser, how big was the universe before the cosmic microwave background, approximately 380,000 years after the Big Bang? How can we constantly get photons from that moment? Shouldn't we expect to see a stop of the flow of photons from the moment the universe became transparent sometime in the future? Can't imagine why the shockwave from that instant is constantly arriving at us. The cosmic microwave background radiation, that was the time when the universe had like just cooled down enough, 380,000 years after the Big Bang, that light itself could finally sort of escape out into the universe. And so when we look out into the cosmos in all directions, we're seeing this afterglow of the Big Bang, but we are 13.7 billion years after it happened. And the crazy thing is that now those regions where that light left, they're now 43 billion light years away from us in all directions. And so the photon, the individual photon that finally was able to escape after the Big Bang, left 13.7 billion years ago, has traveled to us across that space while the space itself is expanding. So back when this happened, when the cosmic microwave background was released, the size of the universe at the time, the observable universe, was 43 million light years across. And now it's 92 billion light years across, so a much big difference. So why can we see that, right? It's important to understand that the universe isn't this sort of, the Big Bang wasn't this explosion from one place, and you're seeing this kind of explosion, this shock wave. It is this stretching. Just imagine space was more dense, perhaps infinite, and then it stretched, and now it's less dense. And so anywhere that you go, you're going to see that stretching, and you're going to see those photons travel that immense distance. They've been traveling for 13.7 billion years to make that journey to you in all directions, which is just a mind-blowing idea. Possible cinema. I'm wondering, what do you think about the moral, ethical implications of our species conducting a self-induced panspermia by, for example, sending thousands of probes with organic materials to exoplanets with known habitable zones in order to potentially kickstart life there? If plausible, what do you think about the type of impregnation of the universe by us? Such pollution is bad when you look at other examples of life, but what about giving a better chance for life to thrive, taking the next billions of years into account? Welcome to the future conundrums that are going to face, future conundrums that face humanity if we ever get to a point that we are actually able to send probes to other stars. We're going to deal with a minor version of that here in the solar system. What if we find that there's life on Mars? What if we find there's life on Europa and Enceladus? Do we send probes there and potentially infect those worlds and kill off the native life forms that are there? I'm here on Vancouver Island. I'm surrounded by various invasive species. Every spring we try to go out and cut down all of the Scotch broom before it blooms and spreads across our landscape. So my feeling is that if we discover that there's life on other worlds out there, that we find that there are other planets, inhabitable zones, and there is life there, then we need to respect that life and do whatever we can to not infect it with our Earth life. But at the same time, I think we're probably going to find at this point that a lot of the universe is empty. We don't see any evidence of life. This is what the Fermi paradox is all about. And if it is truly empty, then I don't think there's any problem with us going and spreading life out there. I think life is more interesting than non-life. That trees are more interesting than rocks. I apologize to the geologists out there. So I think it all just comes down to whether we can know if there's life there. And I think where we're gonna screw this up, the way we always do, is that we're gonna take shortcuts. We're gonna go, I don't really want to check. It's too much work. It's too expensive. Let's just send a spacecraft that's going to have the ability to seed life on a world. And if it just finds a world, it just seeds the life and just moves on. And then billions of years from now, we show up and who cares? Not our problem. That's That's what we're probably going to do. But I think if there is life on an extrasolar planet, then it is unethical for us to seed it with life. And if there isn't life, then we can do whatever we want, tear it apart, turn it into Dyson spheres, whatever, who cares? Rocks are rocks. But we can't be lazy about it. We've got to check and we've got to be sure. And that's going to be the hard part. Connor Paller. You're just feeding flat earthers. They'll take so much of this so far out of context, it's not even funny. This was in response to an episode that I did about whether you can send probes up in the solar system, right? Because the plane of the ecliptic is this flat disk and all the planets are orbiting in it, and but you can imagine, you know, sending spacecraft up to sort of view things from above, and there's not a lot of interesting things up there. I don't care what flat earthers think. They're trolling, and they will take all kinds of things out of context. So who cares what they think? Gabriel R. The planets travel on a flattish disk, but I've seen the Oort Cloud portrayed as spherical. Why the difference of shape? So astronomers think that the Oort Cloud, right, this is this cloud of icy objects that extends like a really long way, like up to 2 light years away from the sun, pretty much half the distance from the sun to the nearest star. This cloud of icy debris is out there. And they think that it's spherical because comets come into the inner solar system at totally random directions, not from the plane of the ecliptic, but in all kinds of weird directions. And that tells them that it's probably this sphere. So why is it spherical and not flattened like the rest of the solar system? And it's because these things are so far away. The amount of gravity that they're experiencing is really small, and they're getting jostled by all the other stars that are in the Milky Way. And any one of those stars, as they pass nearby, can perturb some of the orbits of these Oort Cloud objects, and they'll interact with each other and sort of spread out into this more spherical shape. Once you get closer in to the inner solar system, then you've got that dominant gravity coming from the sun, and things remain in that plane of the ecliptic. But you get far enough away and things will start to, you know, it's a lot more fast and loose with gravity. Boycott Google. When there's an active galactic nucleus quasar with lots of stuff falling in and piling up, will the layers closest to the black hole be made up of neutronium or even quark star core matter, if that exists? Will the layers a bit further out do nuclear fusion? Imagine it like a 2-dimensional huge star with a black hole at the center. For those who don't know, a quasar is essentially an actively feeding supermassive black hole. So imagine a black hole, there's one at the heart of the Milky Way with 4 million times the mass of the sun. And let's imagine lots of material was falling into that black hole and it was too much for it to be able to feed on. That material would rotate around it and form this big accretion disk. And then these big magnetic fields sort of sweep around within this material, and it causes these jets to blast out of the top and the bottom of the black hole. And so when we see quasars, we see these really bright objects that seem like stars, but what they really are is this jet of material coming off of a supermassive black hole. So in that environment that's around a supermassive black hole that is actively feeding, you know, the quasar, you actually get this stellar material piling up in a way that it's so hot and it's so dense that it does become like the core of a star. And that's why they're so bright, is because you've actually got nuclear fusion, you've got, you know, all of this, these stars have been just like torn apart and mashed up and turned into a star disk around the black hole. And then it all gets gobbled up by the supermassive black hole. But yeah, for a while there, you've got conditions that are like a star, and that's why they're so bright. A supermassive black hole, when it's actively feeding, can let out more radiation than the rest of the entire galaxy combined. Evolution Inc. Hey, I recently listened to Ringworld, and I'm just wondering if such a large structure possible to build, and if we could, would it be stable? I mean, if we dismantled the asteroid Kuiper Belt, would we even have enough resources, or would we have to destroy a small planet like Mercury? Larry Niven is one of my favorite science fiction writers. I really enjoyed Ringworld, and Larry Niven realized that he had made a mistake with the Ringworld novels. The problem is the Ringworld isn't stable. And so he did a follow-up novel called The Ringworld Engineers, where he explained how the Ringworlds remain in their position that they're in. So here's the thing. When you have one object, let's say the Earth, right? The Earth is orbiting the sun at the middle of the solar system. And the Earth is going 30 kilometers per second in orbit around the sun. And so the motion of the Earth balances out the gravitational force that's pulling it inward, and it remains in its orbit because it's not running into anything. It just goes around and around the sun for, ever. But if you build a solid ring, you no longer have something that is in orbit. What you have is a sort of a structure that's just hanging there. And now it doesn't have that perfectly balanced force that's keeping it in its orbit. And so the ring is going to slowly drift back and forth because the interactions with other objects in the solar system, with other stars, with flares on the star, different densities on the ring, and eventually it's going to drift a little bit out, and then it's going to get these oscillations, and then it's just going to, crash or tear itself apart. And Larry didn't even realize this, and so in the Ringworld engineers, he has these thrusters on the inside of the Ringworld, and it's constantly watching for the position of the Ringworld and sort of puts it back into this sort of perfect balance. And it's the same problem with a Dyson sphere. If you have an actual Dyson sphere, once you form that full sphere, it's going to hang there around the star, and then it's going to oscillate around, and then it's going to bonk into it. So that's why even Dyson knew that it probably wouldn't be a sphere, it would probably be a swarm. And so a swarm, you've got trillions of individual satellites, each which is in its own orbit around the sun, and that is stable because each of these satellites is just going around the sun. It's when you try to fashion it into some kind of rigid structure that you get into a problem. Now, is there enough material? There absolutely is. If you dismantled all of the planets, Kuiper Belt objects, asteroids, everything, you could build a Dyson sphere around the sun with a thickness of about 20 centimeters. So there is enough material there to do it. Not that we know something strong enough that could handle it, but you can imagine you dismantle all of the planets in the solar system, you build them into a bunch of O'Neill cylinders, you set them all rotating around the sun, and you've built this Dyson swarm of all that material, and you could house trillions or quadrillions of people on these structures. And if you wanted to go from one cylinder to another one, you could hop in your spacecraft and have to fly over to it. So it's not quite a perfect Dyson sphere, but it would allow a lot of people to live in the solar system. Astro B. Hey Fraser, you often talk about moving heavy industry into space to cut pollution and damage on Earth. Surely this is unachievable because of the huge difficulty of moving heavy stuff out of Earth's gravity well. If the plan were to shut down terrestrial production and move it to mined and processed asteroid material, the problem would be huge for sending things down to Earth for use. Even creating the machinery and equipment operating in space is well beyond our ability. To do this for Mars or the Moon is even less feasible. Would you agree that such production systems are hundreds or thousands of years off from what we have today? It's all about its scale. We as human beings have this way of starting with something really simple, figuring it out, and then scaling it up and up and up and up. When you look at, say, the transportation system or the way air travel works or cities, it baffles your mind to think, oh, there could be a place that is kilometers and kilometers across with buildings that are hundreds of meters tall, and that could ever be done. And yet, when you think about modern cities, they're often built within less than 100 years. So will we ever do it? I think the way this is going to work is that the infrastructure will bootstrap it up one step at a time. The first spacecraft that will go there will, they'll start to learn to build some elements, they'll build factories, they'll be able to pull some material together, they'll use that to build better factories, better instruments, they'll refine their techniques. And I think over the decades, I don't think it'll be hundreds of years, but I'll bet you within 100 years from now, there will be a much more significant infrastructure in space that is completely in situ, right? It's all done just based on resources that you can find in space. And actually, I'm going to do an episode about sort of how that process would happen. So stay tuned. Grant Lanning. Do we even have trained astronauts for lunar or Mars missions? By this I mean astronauts with geology and structural engineering backgrounds to study these new environments to make paths for the future more experimental-based scientific astronauts. This was kind of the error that we had made before when we were going to the moon. We sent test pilots who were incredibly brave, and I don't want to sound like I'm putting what they did down in any sense, but what more could we have learned had the first man to walk on the moon been a geologist or any kind of planetary scientist instead? That's a great question, but tell you what, why don't we get an astronaut to answer it? So here is former astronaut Mike Massimino. He was the guy who repaired the Hubble Space Telescope twice. So he has an engineering background. He's the perfect guy to answer this question.
Well, there's I guess a couple things. We do have a geologist in space right now. My friend Drew Feustel is a PhD in geology, and we have lots of engineers. But if we were just counting on the astronauts to do all that work, you'd be in a lot of trouble. You need a lot of smart people, like thousands of them, to figure that stuff out. So I think being an astronaut is more that you have something you can contribute, but that also you're able to be trained in these different disciplines. So certainly having a geologist on a lunar expedition would be a good thing, but you may not actually have a geologist available. We did send one geologist to the moon. That was Harrison Schmitt. That was great. But the other people we sent were not geologists, and they were trained to be geologists. And so I think that for an astronaut, that's what's probably more important. You have something that you can contribute to the program, but you also have the ability to learn about all this other stuff. So it's probably not going to be an army of geologists. You may have one, or may not even have one, but you'll have the people who can be trained to do that work.
Thanks, Mike. That was awesome. Now, if you want to watch a longer interview with Mike Massimino, he joined us on the Weekly Space Hangout this week, and you'll be able to see me interview him. He'll talk about his experience repairing the Hubble Space Telescope, working on this new documentary called One Strange Rock, and what it's like to be in space. So check out the Weekly Space Hangout. I'll put a link in the end of the video. And that's it for this week's question show. As always, thank you everybody for sending in your questions. If you have any question while you're watching this or any other video pops into your brain, just write it down on any video. I will gather them up and I'll answer them here. All right, I'll see you next week.